Okay, moving on to the second part of chapter 14. So we're going to go into our last two organic compounds, amines and amides. Amines are derivatives of ammonia. So I'm going to want you to remember a few facts about ammonia. For example, that was a weak base that I wanted you to memorize. Amines contain a nitrogen attached to one or more alkyl or aromatic groups. So on your information sheet, the generic form we're showing you for an amine has an R group to a nitrogen, and then we're not showing you what is on the other end of these two bonds. So this is what's on your information sheet. And the reason we just have these two lines coming off is because in this particular example, the two lines, the two bonds are going to two hydrogens. But in this particular example over here, the nitrogen, one of those lines is going to another R group, and one of them is going to a hydrogen. You can also have a nitrogen with 3 R groups, okay? So to be an organic amine, it's got to have at least 1 R group. And here we have our nitrogen bonded to an aromatic ring. So those are kind of the ways you'll see an amine. Amines react as bases, just like ammonia reacts as a base. So here's the reaction we talked about when we were in the acid-base chapter. So ammonia, and remember nitrogen is content with just 3 bonds. So if I drew out the Lewis structure here for ammonia, it would have these lone electrons up there. So we often see nitrogen with 3 bonds. But the fact that it has this lone pair of electrons here means that it can accept a hydrogen ion. So if you remember, we had 2 definitions of a base. It could donate a hydroxide, the OH minus, or it could accept a hydrogen ion. So in this particular case, ammonia and amines accept a hydrogen ion on this lone pair of electrons. And in that case, you're going to see nitrogen with 4 bonds. So ammonia will react with water. And the ammonia is a base, so it accepts a hydrogen ion and becomes NH4 with the plus sign. And water is acting as the acid in this case, where it donates a hydrogen ion, so you're left with the hydroxide ion. So we're going to build on that reaction that you already know. So here is our amine. The nitrogen has 3 bonds, and then this lone pair of electrons here. When it reacts with water, the water will donate a hydrogen ion to it. And then our nitrogen will then have 4 bonds to it and have the plus sign, and you'll have hydroxide left over. So very similar to what you've seen with ammonia. Once again, it's a weak base, so you get that arrow going in 2 directions, indicating that it reaches an equilibrium. Neutralization of amines will form what we call an amine salt. So an amine salt forms when an amine is neutralized by an acid. In this picture over here, fish, one of the odors that you smell when you have fish is an amine. And so what some people will often do is squirt lemon on it, because lemon is an acid. And so it'll neutralize that fishy smell sometimes, because it's neutralizing the amine. Amine salts are named by replacing the amine part of the name with ammonium, followed by the name of the negative ion. Now, I'm not going to ask you to name any amine salts, but sometimes you'll come across it here in your reading. So this right here is methylamine, because meth means it's got 1 carbon, and then the amine means it has this amine group on it. So here is my weak base, methylamine. It's going to react with HCl. So the HCl acid is going to donate a hydrogen ion, and that hydrogen ion is going to go and bond to the nitrogen. So now here on the left I have nitrogen with 2 hydrogens, but on the right my nitrogen is going to have 3 hydrogens, because it accepted that hydrogen from the HCl. When it gains that hydrogen ion, it also gains that positive 1 charge. And then you have the chloride anion that was the result of this HCl losing its hydrogen ion. So this is the ammonium salt. So it's methyl ammonium chloride is the name of this, but I won't ask you to name it. I will ask you, however, to write the reactions. So for example, I might give you these 2 reactants, and you have to write the products. There is a subgroup of amines called alkaloids, and alkaloids are physiologically active nitrogen-containing compounds. And so I'm going to take you through several of these. I'm not going to ask you any specific questions on these different ones that I'm going to take you through, but I do want you to know that alkaloids are amines, and that they are physiologically active molecules in our bodies. I do want you to know that alkaloids are usually obtained from plants. Okay? Alkaloids are used as anesthetics, antidepressants, stimulants such as caffeine, and often alkaloids are addictive. So I'm going to take us through some just for the fun of it. The first one is cocaine, which is sold illegally as the amine salt. So the first one here on the left is the cocaine, and here is the salt. So here is the ammonia, the amine that had accepted this hydrogen ion and became positively charged. And so here's the chloride salt. So this is cocaine. If you react with cocaine with sodium hydroxide, that gives us this free amine, where it's no longer a salt and it's no longer charged. And this molecule is what we know as crack. Here's the molecule of caffeine. It's a stimulant of the central nervous system. It's found in coffee beans, tea, chocolate soft drinks, and as many of us know, it's addictive also. Nicotine increases the adrenaline levels in the blood. It is the actual molecule that causes the addiction to tobacco. And the last alkaloid we're going to look at here is morphine and codeine. Morphine and codeine are alkaloids. They're obtained from the oriental poppy plant. And there's a picture of it there. Used as painkillers. It is modified to make heroin. So here are the two pictures of morphine and codeine. Okay, moving on to our last organic functional group we're going to look at in this class, which are the amides. An amide is an amine group next to a carbonyl group. Okay, so that's the biggie to look for when you're trying to identify an amide. So in amides, the amino group replaces the hydroxyl group on a carboxylic acid. So they look very similar to a carboxylic acid. So here's our carboxylic acid with our carboxyl group. And if you just replace this hydroxyl group with an amine group, that's what makes our amide. Okay. What I do when I try to identify my amide is I look first for this carbonyl group, and if it is bonded to a nitrogen, then that's going to be the indicator you have an amide. So some amides in health and medicine. These next few slides I'm going to take you through some common amide compounds, but I'm not going to ask you any of these, for test questions. So urea is the end product of protein metabolism. So make sure you can identify it as an amide. So here is the carbonyl group, and it's bonded to a nitrogen. So that's how we know it's an amide. Actually, I was supposed to be focusing on urea over here. So here's how we know that urea is an amide. This one over here is saccharin, which we use as an artificial sweetener. And both of those are amides. Here's a couple more amides. Some amides such as phenobarbital, nebutol, seconal, or barbiturates. So here's a picture of phenobarbital. And do you agree it's an amide? So this one actually you can either go to either one of these carbonyl groups, but a carbonyl group bonded to a nitrogen is our indicator that we have an amide. Acetaminophen is used to reduce fevers and pain, so if you've ever wondered what that molecule looked like. And can you identify the amide group? And that would be right here. Carbonyl group bonded to the nitrogen. And like esters, where you had to memorize esters went through two reactions, acid hydrolysis and base hydrolysis, amides are going to do the same thing. They're going to go through an acid hydrolysis and a base hydrolysis. So once again, I mentioned this before, but hydrolysis is the breaking apart of large molecules into smaller pieces using water. Okay. This reaction right here, where we take our amide and we do acid hydrolysis, this one, in my opinion, is the hardest reaction you're going to have this term. And the reason why is because it is a two-step reaction. And the reason why is because of this important note on the bottom. Remember that carboxylic acids react with bases, and ammonias and amines react with acids. Okay, so acids and bases are going to react together. Well, when you start off in this step here, and I'm going to show you this reaction, but as soon as you break this molecule here, this amide, you're going to end up in an acid hydrolysis. You're going to end up with ammonia. And ammonia is not going to be able to exist in a beaker with hydrochloric acid. So that's going to go on and do another reaction where the ammonia reacts with the HCl. So that's why over here, instead of just getting ammonia, we get this ammonium chloride salt. So you're going to have to remember this is a two-step process. When you do base hydrolysis of an amide, it's just going to be our usual general pattern, where we rope off the two pieces and we switch what's in the circles pattern. So here's our general reaction pattern, just to refresh your memory. It's double replacement, where we're just going to switch partners. So carboxylic acids are going to they're going to undergo these double replacements when you're reacting them with an alcohol. Okay, that's important that you remember. They don't do this general pattern when you're putting them in water or reacting them with a base. Okay, in those two cases, the carboxylic acid's just going to donate its hydrogen ion. But when you react a carboxylic acid with an alcohol, that's where you're going to do this general reaction pattern. Esters, you're going to break them here between the carbonyl group and the O. And for amides, you're going to break them between the carbonyl group and the nitrogen. Okay, so that's step one. Find the carbonyl containing compound, break off the piece that's attached to the carbonyl carbon. So this is going to be the pieces we break off. Okay, in the second step, so then you look at the second molecule, which I'm not showing you here. Well, I guess we could look at this guy. In the second molecule that's going to contain either an OH or an NH, you're going to break off the piece that's attached to the H. So in this particular reaction, we're going to break it here. So basically circle everything except that H that was bonded to the oxygen or the nitrogen. And then in the third step, you're just going to swap places between what you have circled. Okay, so that's our general reaction pattern. So hydrolysis of esters and amides. Once again, hydrolysis is the breaking apart of a molecule using water. For esters and amides, it's the reverse reaction of the reaction that formed them. So, for example, esterification is the reaction that forms an ester. So the hydrolysis of an ester gets you back to the reverse of the esterification. So just to refresh your memory, we already went over this with esters in the last lecture. But when you have an ester and you're going to do water hydrolysis, or how should I say this, hydrolysis with an acid catalyst, so acid catalyzed hydrolysis, you break between the carbonyl carbon, and you break off this group. You go to the second molecule and you circle everything except the hydrogen, and then you trade places between these two circles. And then you're going to get your carboxylic acid and your alcohol back. Okay. When you're looking at an amine, it's going to be the exact same thing. So we're going to break it between the carbonyl carbon, and so we're going to circle this group, come over here, circle everything except the hydrogen, and then swap places between these two circles. So, but once again, remember, when you're doing this reaction, tell yourself, oh, this is the hard one, this is the two-stepper. When you have an amide and you are reacting that with water and an acid, you have to remember that this amide is a base. And so it is going to go and react with your acid catalyst. Okay, so you're just going to swap places. So start off writing your CH3 and then your carbonyl group right here. So CH3, carbonyl group, you're getting to where you had the circle before, so instead of writing this nitrogen, you're going to come over here and write the OH, because that's what's in the second circle. And then write your H down, and as you're working this from left to right, you reach a circle, so instead of writing the OH, you write down what's in your other circle. Okay, this is our two-stepper right here. So we are going to find which one of these is the amine, and that is this one. This one is the amine. So it is going to react with whatever acid you have here. I'm not actually showing you what acid, I'm just giving you that simplified symbol for an acid. So in this particular case, when all I have for you is the H+, you're just going to come over here and put it with the nitrogen. So right now this amine has 2 hydrogens, but notice down here it has 3 hydrogens and that plus sign. You just write that plus sign somewhere by the nitrogen. If this had been like HCl, then you would just write your chloride ion somewhere near this plus sign. Okay, and that would form your amine salt. And you don't do anything with the carboxylic acid that's formed, because carboxylic acids and acids aren't going to react with each other. So after hydrolysis, the amine reacts with your acid, since amines are bases, is what it's saying there. So here is a learning check, and I have a hint for you down here. Before you tackle this problem, expand out your amide structure so you know how the atoms are attached, so you know exactly what bonds you're going to break. And then after you do that, rewrite the water as HOH. So I always kind of recommend doing that right off the bat when I give you a reaction to write the products. So on your test, your part B is going to be very similar to this. where I'm going to give you two reactants and you have to come over here and write the products. Okay, so if I expanded this out, basically this hydrogen, which is just written in this row, is really bonded to the nitrogen. I could either write it up or down. And then this nitrogen is bonded to the carbon. Okay, so step one, find the compound that contains the carbonyl group. So that would be this group. And then it tells you to break between the carbon and the nitrogen, or the carbon and the oxygen. Okay, so that means we're going to break it here, and I'm going to just finish the circle that it does not contain the carbonyl group. And then you come over to the other molecule and you circle everything except the hydrogen. And then we're going to swap places between these two circles. So if I write this thing from left to right, I'm going to start here and I've got the circle. Well, I can't write this circle, I have to write the other circle, and I have to think about, am I going to flip this circle over? Well, sure enough, I need this oxygen, which is now unhappy because I broke this bond here. I need this oxygen to be written next to this carbon. So I'm going to flip over my OH and write it as HO, because then I can get that oxygen next to the carbonyl carbon. And then I'm just going to finish this group off. So I worked it from left to right. I wrote my circle first, which was my HO, and then I finished it off with my carbonyl group and the CH3. Now I come to this guy and I work it from left to right, so I've got my hydrogen. I'm going to put that hydrogen down first. That hydrogen is looking for something to bond to, so it's going to be whatever's in this circle. Am I going to write it like this? Am I going to put a CH3 right here? No, the CH3 is content. I didn't dissatisfy that carbon here when I broke the bond here. So it's the nitrogen that's looking for something to bond to. So I have to flip this over to put the nitrogen and then the CH3, and then you can either put this hydrogen up, down, or you could even write it just right to the right of the nitrogen in the long group there. If this was a multiple choice test, they would actually put these two hydrogens together and they might write it like this, NH2CH3. So you'd want to be able to see both of these as the same thing. Okay, so that was hydrolysis with an acid catalyst. Now I'm going to focus on if you have a base catalyst. So if hydrolysis of an ester or an amide is done with a base, such as sodium hydroxide or potassium hydroxide, the process is called saponification, which means soap making, since the soap is a product. So as a refresher, here's an ester group. So you break between the carbonyl carbon and the oxygen, and in your second molecule you break between the hydrogen and the oxygen, and you circle off the two groups that you've broken off and you swap places. So we went through this with ester hydrolysis. It's going to be the exact same thing with the amides. So step one, find your compound that contains your carbonyl group. That would be right here. And then it tells you to break between the carbon and the nitrogen. So then we're going to break it here and we're going to circle off everything that breaks off. Then step two, go to your second molecule and break off everything except the hydrogen. So that's why we're circling this one. And then we're going to trade places. So as I write this guy from left to right, you might find a better way that works for you when you go to write the products. This is just how my brain works. I kind of just start off from the left and I would write my CH3 and my carbonyl group. So I would have this part written. And then I go to write what's next, but as I'm going to write what's next, I'm into that circle. So I'm going to write what's in the other circle, and I have to ask myself, do I have to flip it over? Am I going to write it as NaO or am I going to write it as ONA? And you have to flip it over. Remember, you cannot have the Na in the middle of a molecule. It's the oxygen that broke its octet when I broke this, so the oxygen is looking for something to bond to. So I flipped it over, and then I go to my next molecule, and as I work it from left to right, I have the circle first. So I'm going to write this circle, and I know that I'm going to have this hydrogen over here, and I know that hydrogen needs to be bonded to the nitrogen, because that's the nitrogen I broke its octet. So I flip this guy over, and here is the circle that I flipped over, this one. Once again, you can write these products flipped totally different. So if you had wrote them to where they were totally flipped the other way, that would be totally fine. All right, so here's a learning check for you. Once again, I might write this hydrogen down here or up and think of this as just my nitrogen to the carbon bond. So step one, break it here and circle off the group that's going to break off. Step two, go to the other molecule and break off everything except the hydrogen. And then I'm going to trade places between these circles. So I am going to, instead of writing this circle, I am going to write my other circle, NaO. And then I'm going to write this. Do I have to flip this guy over? No, I need this carbonyl carbon next to my oxygen. And then the CH3. And then I go to this guy, and I have, as I work it from left to right, I have the circle. So I'm going to write what's in the circle. CH3, N. And I can write this H down or up, or I could just write it here next to it if I want. And after that comes this H. So I can write it as CH2 if I want. Okay. The last section we're going to go over is talking about the solubility and boiling points of organic molecules. Now, I know for those of you who've been reading your chapters in the book, they've talked about this a little bit each chapter, but we're trying to simplify this for you. So we've kind of come up with some general rules that we're going to stick with for all organic compounds. Okay, it's a little bit more complicated than that, but we're just going to, give you the general kind of idea. So, in terms of whether the organic molecule is soluble, or referring to does it have a high boiling point or low boiling point relatively. So here's what you're going to do. Before we talk about that, I want to talk about assigning polarity to your organic molecules. So for starters, if all you have is a hydrocarbon, so your molecule just has carbon and hydrogens, you're going to assign that as nonpolar, which I usually write as a capital N, capital P. Okay? If your molecule contains an oxygen or a nitrogen, then we're going to say that that is a polar molecule. Okay, so nonpolar if it's just a hydrocarbon, polar if you see an oxygen and nitrogen. If that oxygen happens to be bonded to a hydrogen, or the nitrogen is bonded to a hydrogen, that means that molecule can hydrogen bond, and we are going to label that one very polar. So if it has an OH or an NH, it's very polar. If it just has an oxygen and a nitrogen that's not bonded to a hydrogen, we're just going to say it's polar. And only carbon and hydrogen is nonpolar. Okay, so that'll be your first thought process. And then you need to know this important thought, that as the polarity of the molecule increases, the boiling point increases, and the water solubility increases. So increase polarity, this is what I'd memorize, increases the boiling point, and it also increases the solubility. Okay. So that's kind of the first thing you think about when you're given a boiling point or a solubility question. Okay, so focusing on water solubility. Polar and nonpolar do not mix. Remember we talked about likes dissolve likes, and oil and water don't mix because water is polar and oil is nonpolar. So molecules that contain oxygen and nitrogen, which we said were going to be polar, and have 1 to 3 carbons are going to be soluble. So you want to memorize that. Okay, if your molecule has oxygen and nitrogen and has 1, 2, or 3 carbons, you're going to say it's soluble. If it has 4 or more carbons, it's going to be non-soluble. Okay, and here's a couple pictures. So here is methanol, and methanol has this OH group, so it is very polar. And so since it can hydrogen bond, it's going to want to hydrogen bond to water and become soluble. But the more carbons you put on here, the less soluble it becomes, because this starts acting more like a hydrocarbon. Okay, so there's a limit to how many carbons water can pull down into the solution with it. And we're going to simplify it for this class, and we're going to say 3 is going to be the limit. Okay, so here's diethyl ether. Oops. So here's the oxygen, so we're going to say this is polar because it's got the oxygen here, and it only is bonded to 2 carbons. So if your molecule contains oxygen or nitrogen and it has 3 or less, you're going to say it's polar. So since this has 2 carbons, we're going to say it's soluble. Okay, soluble. This guy right here is nitrogen, and it only has 1 carbon, so we're going to say this one is soluble. This particular one here can hydrogen bond, because remember, nitrogen to a hydrogen or oxygen to a hydrogen can hydrogen bond, so this one's actually very soluble. Okay, memorize that. As the number of carbon atoms increase in a molecule, it becomes more like a hydrocarbon. Therefore, the water solubility is going to decrease. So the more carbons you put on, the less soluble it is, basically. Okay, focusing on boiling points. Nonpolar molecules have weak attractions among themselves, and thus they have very low boiling points. So a nonpolar molecule and another nonpolar molecule don't stick together very strongly. Their attractive force is very weak. So because of that, it doesn't take much energy to turn them into a vapor, to boil them. Polar molecules have stronger attractions, so that's the dipole-dipole attractions. So they have a higher boiling point compared to the nonpolar. And then your very polar molecules, those that can hydrogen bond, have strong attractions. Those attractions are called hydrogen bonding, we learned. And molecules that can hydrogen bond have a pretty high boiling point. Okay, so basically, as your polarity increases, the boiling point is going to increase, like I had said before. So here's an example looking at alcohols. Alcohols contain polar OH groups, so we know that that's what makes them an alcohol. Trying to find my pen. So an alcohol is an R group attached to this OH. So they're very polar because they can hydrogen bond. They have higher boiling points than alkanes and ethers. So ethers would be higher than alkanes, but not as high as alcohols. If polar molecules have similar polarity, so remember your first step is to assign the polarity. Increase in polarity increases the boiling point. However, if you are given some molecules that have the same polarity, then our tie-breaking rule is the heavier the molecule is, the higher the boiling point. Okay, now that's opposite than solubility, so you have to be really careful there. Okay, with solubility in water, the more carbons you put on, the less soluble it becomes. Okay, but with boiling point, the more carbons you put on, the heavier the molecule is, and the heavier the molecule is, the harder it is to vaporize it and boil it. Okay, so keep that in mind. So here is an example. Use the principles above to explain the properties in the table below. So let's go ahead and start off by assigning polarity, because that's what I'd like you to do on your exams. So if we looked at this first one, it is just simply a hydrocarbon. So this one we're going to assign as nonpolar. Our next one is also nonpolar because it's just a hydrocarbon. This guy right here contains an oxygen, and that oxygen is not bonded to a hydrogen. Okay, so it is just going to be considered polar. Our second molecule has oxygen, but that oxygen is bonded to a hydrogen, so this can hydrogen bond. So we're going to assign it very polar. Same thing with this one. There's our hydroxyl group, so very polar. Here we have an oxygen that's not bonded to a hydrogen, so we're just going to give it just polar. Okay, so let's look at the boiling points first of all with polarity, because that plays a bigger role than the weight of the molecule. So let me pick some that have 3 different polarities. Let's do these middle 3 right here. Let's compare these middle 3, because we go from nonpolar to polar to very polar, and notice the boiling points increase. As polarity increases, your boiling points increase. I know my arrow's going down, but I wanted you to focus on these numbers. Okay, 69 to 91 to 158, our boiling points increases because the polarity is increasing. Okay, what if I give you a couple molecules that have the same polarity? So let's look at our first 2. This first one, so they're both nonpolar, so you're going to say, okay, the heavier the molecule is, because that's our tie-breaking rule. We have to go to the heavier it is, the higher the boiling point is going to be. And sure enough, if it has 5 carbons, it has a boiling point of 36. But if I tack on, one more carbon, the boiling point goes up to 69. Let's just do that with one more. Let's look at, say, these 2. They're both very polar. But the heavier the molecule is, the higher the boiling point is going to be. All right, in terms of solubility, now we have to remember that whole, if it's polar, it's soluble unless it contains 4 or more carbons. So right off the bat, the nonpolar ones, you're just going to say insoluble. Okay, those are going to be easy. If it's nonpolar, it's insoluble. These last 4, we have said were polar, so we have to go and count their carbons. This first one here has 1, 2, 3, 4, 5, 6 carbons, so it is insoluble because it had 4 or more. My next one, which is very polar, has 1, 2, 3, 4, 5, 6 carbons also, so it's insoluble. This second to the last has 3 carbons, and the last has 3 carbons. So both of those guys are soluble. Okay, 1, 2, or 3 carbons will be soluble as long as you are polar or very polar. All right, so here's a learning check. Predict which molecule below has the highest boiling point. So if it's a boiling point question or a solubility question, I want you to assign polarity first. So we look at this first molecule and it has an OH, which means it can hydrogen bond. So we're going to say it's very polar. Over here I have an oxygen, but it's not to a hydrogen, so this one's just polar. And my last choice is a hydrocarbon, so it's nonpolar. So you're going to memorize as the polarity increases, boiling point increases. So we are going to pick this molecule to have the highest boiling point. Okay, the next question. I'm going to sneeze. Oh, sorry about that. Okay. Predict which molecule below is most soluble in water. So now we have to think about, well, let's first of all assign the polarity, because we know hydrocarbons are not going to be, if it's nonpolar, it's not going to be soluble. So my first one here, I see an OH group, so it's very polar. My second one, I see an OH group. I actually see two OH groups. So the more OH groups you have, the more polar the molecule is going to be. So I'm going to put that this guy is very, very polar. And my next molecule here also has two OH groups. So we'll just go with this very, very polar symbol. Looks funny. So as polarity increases, solubility increases. So between these groups, these last two are going to be more soluble than this first one, because this first one only has one OH group. The more OH groups you have, the more hydrogen bonding you can have going on with the water molecules. Okay, so both of these, so this first one here, remember you start counting carbons if it's a solubility question. This one here has 2 carbons, this has 3 carbons, so we would say both of these are soluble. But the question's asking us which one is most soluble. And remember, the more carbons you have, the less soluble it starts to become. So since this one only has 2 carbons, we're going to say it is more soluble than the molecule with 3 carbons. So here's a note. When there is more than one oxygen or nitrogen in the molecule, there can be more attractions with the water. So molecules with more than 3 carbon atoms can be soluble if you have more than one OH. So the way I kind of like to think about it, I lost my slide there. You're on the very last one. I'll go down here. So the way I like to think about it is for every OH group you have, that can drag 3 carbon atoms approximately into the water solution. So if you think of every OH group can handle 3 carbons in getting it, dissolved, then you can see that the more OH groups you have, the more carbons, the molecule can have and still become soluble. So this is an example of a molecule that has 6 carbons. So this is glucose, one of our monosaccharides. And it's very soluble in water. We all know sugar is pretty soluble in water. So basically, you can break that 3 or less carbons being soluble if you put more OH groups on. All right.